Okay, so the next speaker is Massimo Ruzzene from the University of Colorado at Boulder. And Massimo is another recipient of the 2020 SES Fellow Honor. And the title of his talks is Dynamics and Topology of Non-Hermitian Elastic Lattices with Non-Local Feedback Control Interactions. So the floor is yours, and I'm going to get out of the way.
Okay, thank you, Stefano. And I want to thank the Society of Engineering Science for this honor. It's always a pleasure to attend this conference, even under the unusual circumstances. It's one of my favorite conferences, so I'm very happy to be here and present, and very honored of being a fellow of the Society. So this talk is on dynamics and topology of a class of lattices, which are mechanical lattices, that are endowed with non-local feedback control interactions. So we're studying the wave propagation in these class of lattices because of the control that is added to them have become non-Hermitian, which essentially means that the Hamiltonian governing the motion of these lattices is non-Hermitian. And this is a topic that has gained a lot of interest in recent months or years. And the work is co-authored by Mateus Rosa, who's a PhD student in my group. And it's a mostly theoretical work. We've done it during this time. And so it's almost an exploration of what we can do when we look at a simple mechanical lattice with these non-local control interactions. As I said, this is a fairly active topic of research that relates to non-Hermitian physics. And there's a number of pieces of work that are related to this area. Non-hermeticity is associated with, in some cases, with the presence of loss and gain in the system. And this has been explored to achieve parity time symmetry, which allows unidirectional invisibility of sensors. So the propagation of waves in one direction that are unaffected by the presence of an obstacle in some cases, as the case of a sensor, for instance, that allows the measurement of quantities in a way that the sensor does not disturb them. And in a related topic, non-Hermitian systems can be endowed or can be characterized by the presence of singularities, spectral singularities, which are known as exceptional points. And these have been explored recently in the context of sensing. And as these singularities break down, when the symmetry associated with the parity time symmetry is broken because of the presence of a change in the physical properties of the system. For instance, we've recently studied, as shown here to the right, a setup where we can investigate the presence of an added mass in an elastic waveguide. And this is shown to be very sensitive and as an indicator. So more recently, also, people have looked at the topology of these systems and see how different phases of the material can be induced by looking at these non-reciprocal interactions that may occur that lead to non-hermeticity. And one of the manifestations is so-called the non-Hermitian skin effect, whereby you have vibration modes that localizes at the edge. And that depends on the type of interactions that occur in the system. This has been also looked at from experimental point of views, and the group of Corentin Coulet in the Netherlands has done this 1D systems where he has feedback control in them, and he has shown that this can lead to non-reciprocal wave propagation through the system associated with introduction of gain and loss. And so this has been a basis for our investigations to some extent. And also very recently, we have work from William Irvine and Vincenzo Vitelli. They've looked at two-dimensional systems with these inactive elastic media. So non-Hermitian physics is associated with an active source or in the presence or the presence of dissipation in the system, and a good balance in general between them. Also, very, very recently, this feedback action in a waveguide has been implemented also by Vitelli and Guolan Wang's group in a joint effort where they have investigated a beam waveguide with embedded actuators and sensor in the form of piezoelectric patches that are driven and again in a feedback loop. So based on this kind of line of work, a few months ago, we started looking at how we would, the wave propagation on the system would be affected by the presence of active control in them. So we started with the simplest system that we've been playing with for a while, which is a very simple mechanical system, which one can think of the easier or most bare bone version of a metamaterial or of an elastic waveguide, which essentially consists of masses connected by linear springs. Here, the blue lines are the linear springs, and the masses are allowed to move along the horizontal direction. And the interaction between the masses is given by a linear spring constant K. And then in addition to this, we add a feedback control. So we add a force applied to a mass N that is the result of the deformation or the relative position, the relative displacements of two masses, some unit cells or some masses away, precisely a number of A masses away from the mass under consideration. So A defines what's the delay or the spatial delay of these interactions. So if A equals 0 means that the spring immediately before the mass, so we can define this as a local feedback, but we can also consider it as a non-local feedback as A grows or as we move away from the mass. So the equation of motion looks very simple, but has this additional term that ends up breaking the symmetry of the elastic interactions. So if we consider a lattice with n masses, then we can assemble this set of equations into a matrix form. And if you look at the resulting stiffness matrix, then it becomes non-symmetric. And because of that, the system becomes non-Hermitian. So the dynamic stiffness matrix that results from this, assuming harmonic motion, becomes non-Hermitian. And so this is a class of non-Hermitian system. And what we set up to do is to look at what happens when we have different gains and different non-local interactions. So as we move the force away, the feedback force away from the mass of interest or the analysis mass. So we started studying this as a very simple type of fundamental investigation on what we should expect in these systems. And so the first thing that we did is we tried to derive the dispersion relations for this system that is in the theory, the context of metamaterials or periodic systems is a fairly straightforward, well-established process. And we assume harmonic wave motion, and then we impose a propagation constant to define the spatial evolution of the wave in terms of a constant mu, and then defines the location of the mass. And if we substitute it in the equation of motion, then we get our dispersion relation with the added term that is associated with the presence of the control, feedback control, which is normalized gamma here, normalized relative to the stiffness of the spring. So in this case, then we can look at what happens to the dispersion relation, and we can start looking at the case of local feedback, as mentioned, where A is equal to 0. So the feedback is defined by the relative motion or relative displacements of the two masses attached to the spring. So in this case, then we can see the dispersion relation is kind of interesting. It's compared to the case of the uncontrolled case where we have the dashed line, and then the red line is the control case. So the dispersion relation becomes complex. So it has an imaginary part, which is distinctive of these systems. And the imaginary part is odd relative to the 0 term. So it has a part that is positive for the positive mu, and it becomes negative for negative mu. If we look at the operator that defines the propagation from one cell to the next, a positive imaginary part defines a decaying wave as it propagates from one cell to the next, as opposed to the case where we have a negative imaginary part of the propagation constant of the frequency that leads to a term that is indeed amplifying the wave. So we see that by adding this control, we separate the space whereby the wave propagating to the right are lossy or are decaying in space, whereas the waves propagating to the left are gaining in amplitude. And to simulate this, or to verify this through simulation, we conducted a numerical simulation, and by applying a transient response to a finite chain of masses of 1,500 particles, and then we apply the force in this point about in the middle of the chain, and then we observe that the propagation only goes to the left as a result of this gain. And we can take these response in space and time and take a Fourier transform in 2 dimensions to verify where these falls into the system. And indeed, it goes in here and it shows where the dispersion relation matches the prediction of the theory to show that there's asymmetric wave propagation. So this becomes a non-reciprocal medium that allows propagation only in one direction. And in fact, this direction of propagation allowed is a function of the gain. So in this case, we assume a positive gain, gamma c, equal to 0.1 in this case. But if we make the gain in negative, then we reverse the situation where we flip the imaginary part of the frequency, and then the gain and loss switch in order. And so we have a wave that travels towards the right, amplified, and it's decaying towards the left. So the other thing that we started looking at to go beyond what was done in some of the experimental work earlier before us is, as I said, to look at what happens when you have no local feedback. So we started putting the control action, moving it back by a unit cell. So we set A equals 1. So now we push it back 1 unit. And we observed that now the propagation band for these waves is now becoming, has different zones. Again, we have pink and green to define respectively loss and gain regions. And so in each direction, we have one loss region and one gain region, and those are reversed in the negative propagation. So the propagation is asymmetric, but we have a band where a wave is free to propagate in one direction depending on its frequency. It can travel to the left or to the right, depending to the frequency where we're at. And this is what the simulations show here in this plot, where we have a force and then we apply a transient broadband amplitude that is of this kind. So it's fairly broadband relative to the frequency range that we're looking at. So it almost covers all the frequency range here. And we can see that the wave splits into 2 harmonic components, one traveling to the right and one traveling to the left, which is consistent with the splitting of the propagation regime of these waves into basically two zones. It turns out that the number of zones are a factor or dependent upon how the non-local feedback occurs, so how far we go back. And so if we look at a case where A equals to 3, then we end up with 4 regions we split up. So you can see that the rule becomes now that the number of loss and gain regions within each propagation zone is A equal to A plus 1, where A is the delay or the non-local coefficient defining the interactions. And so this even shows even more and how a multi-component wave gets split up into different components that travel both at different speeds because of the propagation velocities associated with each of these waves, and then in different directions. So you can really see how these different wave packets decompose and separate in their propagation regimes. So the interesting aspects of this is that we can also study this more in detail by looking at the frequency, both the real part and the imaginary part frequency in the complex plane, and see the evolution as the propagation constant varies in this domain, as we vary the propagation constant. And in fact, we can see this as a 3D in a complex plane becomes a 3D curve. And if we project this phase portrait in complex plane on the complex plane where with the axis real and imaginary frequency, we can see that as the propagation constant varies, we develop a loop. So there's a loop going, which in this case, for a constant positive gain, it's a clockwise loop, as shown here. So as we go from mu equal to 0 to mu equal to pi, that defines the propagation regime, or the range of the propagation constants considered. So it turns out that these loop can be associated with a parameter or a winding number that is calculated as an integral of basically this loop. So this is an integral of the derivative of the frequency as a function of the wave number. And so in this case, for a loop that it's clockwise, we get a winding number that happens to be equal to -1. And the winding number is associated or tells us what the type modes we should expect in the system. Specifically, if we look at a finite system of, say, 100 particles, then we can plot the modes, the natural frequencies of these, which happen to be all real in this case. And then if we look at the modes, and we select some of these modes at these frequency location, 1, 2, and 3, and we're looking at the eigenmodes of the eigenvectors of the system, they're all localized towards the left. So a -1 winding number will define is associated, we find that is associated with a localization of all the modes to the left. And this is known or in both quantum mechanics and classical systems, which are non-Hermitian, has been denoted as non-Hermitian skin effect. And we have shown it here in this simple case of the spring mass system. If we flip the order of the sign of the control, then everything gets reversed. And then we have the winding that occurs in a counterclockwise fashion that becomes associated with a positive winding number of equal to 1. And then if you look at the modes happen to now be localized to the right of the domain. And again, so this winding number is essentially a topological invariant associated with the control, and it tells us what types of modes we should expect in the system. So just as a reference, if we have no control, so we have a purely Hermitian case, then the winding number happens to be 0, and the modes are non-localized, and we have no loop in the imaginary part, as the modes are basically purely real and the propagation is purely real. There's no imaginary part. So this is, if you will, our baseline case that we can study. So it is interesting looking at these because it gives us a prediction of what happens in the system, and again, having a non-local interaction then allows us to define multiple regions, and as I said, of gain and loss, and these multiple regions are associated with frequency ranges that have either positive and negative or negative winding number. So for example, in this case, then we have a negative winding number for mode 1 and 2, and they're associated with localized modes at the left boundary of the domain, whereas mode 3 and 4 are within a loop that is it's got a positive, negative winding number, and then they're associated with the right localization of these modes, and so on and so forth. So if we have a non-local parameter, then the behavior of equal to 3, then we have 4 regions, and so we have 4 loops with alternating winding number, and so the behavior becomes more rich, and we have alternating of left and right localized modes as we move from one region to another. So we can explore this further. We'll skip this. One of the interesting things that one could do is to define these as basically material phases, and you can look at these as putting them together, where you have a lattice with a negative control, and then law, and then you couple it with the lattice with the positive control gain, and these are exactly the same except the controls are changing, and so you end up with a combination of the dynamics of these two that combines in ways that are kind of interesting. So you have the loops for the blue sublattice, and then the loops for the red sublattice, And depending on whether they are of in which area you are of the domain, for example, for mode 1, you end up with a lattice that tends, lattice A, that tends to have localization of the modes towards its right, whereas lattice B have localization of the modes towards its left. And so the combination of these two leads to a localized mode at the interface. If you go in between these loops, then you don't have strong localization, so that the two effects combine and compensate each other. But if you go in region 3, then the opposite happens, as opposed to 1, where each lattice tends to localize toward away from the interface, and so on. And so there are also regions which are intermediate between the two. So this gives some thoughts on how interesting or rich these lattices behavior could be. So we then looked at a two-dimensional system, and again, to keep it very simple, we consider this spring mass lattice in two dimensions. And to keep the calculations analytically tractable, we consider the motion of the masses going out of the plane, and then the spring constants are proportional to the relative motion of these neighboring springs. And we can do a lot of, we have a lot of parameters to play with. Here we can have basically, first of all, we can have the spring constants along X and Y to be different or to be the same. And likewise, we can also change the control gains along X and Y as well, and also their locality. So we could change really how these lattices control. And again, this is all theoretical, so it's easy to do and easy to implement. So for simplicity, we kept the constant, the spring constants the same, K, but we did play with the control actions along the two directions. And there's quite an interesting and rich behavior here as well. So if you look at the dispersion relations for these lattice two-dimensional, there are two-dimensional surfaces, and they are represented here as isofrequency contours. So the top one is the real part of the frequency as a function of wave number along X and Y. And the bottom part is the imaginary part of the frequency. So what is noteworthy is that the imaginary part is, again, is anti-symmetric relative to a negative 45-degree line. And so he has positive regions and negative regions. And so if we look at, in particular, what happens at a given frequency. So for example, if we look at a isofrequency contour of 0.7, then we identify a specific circle here in the real part. And then we track what happens to the imaginary part along the circle. We observe a couple of interesting things. First of all, that the upper half of the domain is corresponding to a loss domain. So we can track radial diagrams that show that waves propagating along the plus 45-degree line would be attenuated, whereas waves that are propagating along the negative 45-degree line would be amplified. And waves that are, and this is directional too, because the gain and loss are coefficients, if you want to call them that way, are maximum along the 45-degree line, but then decrease as you move away from that line. And so we can simulate this again to show what that would imply. And you can see here that the waves, if you have a wave in the middle, then it propagates towards the bottom in the negative 45-degree direction, but it doesn't propagate towards the top. And this can be also directed by changing the gains of the controls. And for example, in this case, if we have gamma y, so that's control gain along that is almost the same as the x direction, then it almost propagates at 45-degree or at an angle. But if you change and reduce the control gain, then you also rotate these radial directivity plot accordingly. And so you can have basically a directional gain. And this becomes even more relevant if you look at multiple frequencies at the same time. And then that can be looked at by looking at these isofrequency contours and then tracking the isofrequency contour in the imaginary part of those. And then you can see what's happening there. And so if you look at a frequency of 0.5, which is the circle, then you have loss and gain along the 45-degree line. Look at a 1.75, which is the dashed line. Then you have the loss and gain directions are reversed. And so you have one gain towards the positive, let's say, semi-half plane, whereas you have loss in the negative semi-half plane. But you also see some very clear lobes that are appearing in this case. So you have, there are certain directions where these coefficients are higher than other directions. And this is also very clear in the 2.5 case, where you have a very, very strongly directional response in terms of gain and loss. And again, one can imagine that you have a situation where you have a broadband input, and you apply the broadband input, and then you have the broadband input gets decomposed both in direction and angular direction, and also propagation directions, where you have a low frequency that travels towards the negative 45-degree line, and then you have the mid frequency that goes at 3 angles, and then the highest frequency goes pretty much straight and very condensed and concentrated along the plus 45-degree line. So we're in the process of, I'm not sure how much time I have, but we're in the process of looking at finite strips and how they these localize, and specifically what happens when you have an infinite lattice in the y direction and it's finite in the x direction. And so we're expecting to see edge modes that appear in the along the finite dimensions. Maybe I'll skip quickly on this because there's a lot of combinations of parameters that can play a role. So we have essentially the loops that are corresponding to loss and gain become a function of the propagation constants along y, and so you have a behavior that it's rich in terms of these two propagation constants. And so I'll just quickly show some results where you have basically in alternating regions of scheme modes that are either localized to the left and to the right. And if you combine them judiciously and in a finite lattice, then you could have situations where basically you are able to concentrate the motion and to be localized only along one edge, and it propagates in one direction, and it doesn't travel in the other directions, and so on. So it stays concentrated and localized. So this also allows us to look at mode shapes of completely finite lattice, so that are bounded in both x and y. If we look at the eigenmodes of the system, and then looking at the gain and loss distribution, directional distribution, one can foresee, for example, that these modes become, at this particular frequency, become localized towards an edge, like in this case at the bottom left corner. Again, this is the result of gain and loss and the fact that the energy concentrates there as a result of that, if the domain is finite. And then it goes at a different frequency, it gets concentrated at the top corner. And then there's interesting interactions in the case of 1.63, where you have this complex directional behavior. And then if you look at the steady state response, that it may be characterized by the mode shapes associated with this frequency, then you can see that they're localizing at the edge as a result of the evolution of waves and the onset of vibrations and so on. So the behavior is also fairly complex in terms of what these modes and where these modes end up being. So I think I want to stop it here and provide some conclusions and a brief summary. So we studied this system almost like a toy problem on the lattices. It's what we found as this being the simplest non-hermetic system that we can play with. And we looked at introducing feedback interactions and how these interactions affect wave motion. And we have been interested in wave motion and metamaterials for a while. And this is kind of a new spin to it, where we put some controls in them. And it could open a lot of opportunities as we introduce some control theory in this. But so far, we've just done a very simple feedback control. You can denote it as a proportional control. but it also ties well in with the literature on non-Hermitian systems. And one of the things that, one of the manifestations that we've observed is the presence of these modes that are appearing at the edges and corner that are denoted by the literature and by us now on as non-Hermitian skin effect. This has clearly opens up new possibilities for active materials that can be actuated locally and in a distributed fashion. And one of the things we observe is the ability to really filter waves in novel ways, to separate harmonic components and to split them up and to have really tailored propagation in these. So we're looking at following up with some experiments and looking at real geometries and not spring masses lattices, but we expect that a lot of these behavior will be replicated in higher dimensional geometries. And there's once we can then modulate, introduce modulation and control parameters, then we can also have a lot of freedom in shaping how waves propagate. So I conclude by thanking again the Society for this opportunity. And then this is sponsored by National Science Foundation and the Army Research Office. And Mateus Rosa, shown here, has done all of the simulations shown and a lot of the theoretical work on in this paper. And so I thank him for his contribution. Thank you for the attention, and happy to take any questions you might have.
Thank you, Massimo, for the nice presentation. And thank you, and congratulations again for your selection as SES fellow. There is one question in the pipeline. It says, how can in practice one generate or tune the strength of a non-local interaction, like in the case of metamaterials, or if you have any other applications in mind?
Yeah, so I think we, as mentioned in the literature review, there's been work that has been denoted as robotic metamaterials. Corentin Coulet has done this by adding motors in terms inside a chain of, you can call them resonators if you will, but so he has done that effectively. And then the other work that we're also pursuing, but has been recently come out on the archives by Vincenzo Vitali and Guolan Wang. They've used a beam type systems with piezoelectric patches, and so one can envision, or they have implemented the system where the piezo patches are actuated based on measurements of strain somewhere else along the beam, and so that breaks the symmetry because of propagation. It breaks the symmetry of the constitutive equation that results from it, and so that leads to the non-Hermitian effect. So there are other ways. I think it does require active means, of course, because you have active control. And so this may be just an exercise in futility, if you will, but I think there are opportunities for doing experiments on this and potential applications.
Right. So I don't see another question. Let's wait, because before I skipped one, so I need to make sure I don't do that. So let's wait a minute. I have a question in the meanwhile. So at the beginning, when you were showing the dispersion relation, you were saying that the effect of the control is mostly seen at the in the imaginary part. So you have this attenuation, while the real part had maybe no correction or milder correction. But then I saw that in the cases where you were having non-locality, all of a sudden the morphology of the branch, even the real part, was starting to be affected. Can you comment a little bit on when that kicks in?
Yeah, and I think we've observed the same thing. I don't know, why that is. I think that's what comes out of the calculation. I think it's it becomes like having non-nearest neighbor interaction, and I think we know that non-nearest neighbor interaction affect the shape of the dispersion curve, even in the case of a symmetric system. And so I would imagine that that's what happens there. It's like if you had a spring that reaches out further to units that are the ones that you're looking at, and so we know that affects how the dispersion is shaped. And so that affects the wave velocities and so on. So that's what I would expect to see. And that's kind of what I explained in terms of why that curve changes.
All right, thank you. And I don't see other questions. Therefore, I just thank you now. And I guess we're ready for the next speaker.
Okay, thank you, Stefano. Thank you, everybody. I suppose
Yes,
I'm
yes,
leaving, right? I click leave on the